Okay, so this is our second lecture, and this is all about evaluating limits analytically. So this is section 1.3, evaluating limits. Okay, so in the last lecture, we observed that the behavior of the limit of a function as x approaches c doesn't necessarily depend on the function's value at x equals c. So let's just start by recalling that. So the limit as x approaches c of f of x does not depend on the value of f of x at x equals to c. Okay. But in certain cases, the limit does equal the value. So sometimes this does happen. So if the limit as x approaches c of f of x equals f of c, then we say that f is well behaved at x equals c. In other words, f of x is continuous. And we'll learn the formal definition of continuity in the next section. But just for now, if the limit as x approaches c of f of x equals f evaluated at c, then that's another way of saying that f is continuous at x equals c. Okay, so let's start with the theorem. So theorem 1.1. Okay, so if A and, or say if B and C are real numbers, and N is a positive integer, then we have several parts. We have part one, the limit as x approaches c of the constant function b is equal to b. Part two, the limit as x approaches c of x is equal to c. And then part three, the limit as x approaches c of x to the power n is equal to c to the power n. Okay. So part one is kind of obvious, the proof of that. Again, if we were doing it formally, we would use an epsilon delta proof. But just thinking about it, so for part one, if this is like b, right? Then this is your function f of x equals to b, and say c is right here. If we head towards c from this direction, the value of the function is always going to approach b. And if we head towards c from this direction, again, the value of the function is always approaching b. So informally, that's a general argument for part one. So maybe we can look at an actual formal proof for part two. So to get the proof part two. Okay. So we want to show that this satisfies that epsilon delta definition of the limit. So maybe we should recall that. So recall the limit as x approaches c of f of x equals to L if for all epsilon greater than 0, there exists delta greater than 0, so that if the distance from x to c is less than delta, then the distance from f of that x minus L is less than epsilon. So that's the formal definition of the limit from last time. Okay, and we want to use that formal definition just to argue why this is true. So we want, so what do we want in this case? So we want so x right here, that's our function, right? Like this right here, that's our f of x in this case. So we want f of x minus L to be less than epsilon for any positive number epsilon. So that f in this statement here is just x. So we want x minus L to be less than epsilon. Okay. So far, so good, that's what we want. Now, this proof, I'm looking through the textbook right now. This proof is on page, oh, wait a minute. Yeah, so section 1.3.
63.
Yes, on page 63. Okay. So you can go through this again in your own notes, but okay, so that's my function f, and then this is like the c is my limit L. But plugging into this definition we want to satisfy, we want that whenever this is satisfied, x minus c is less than delta, right? But we see that we already have it, so if we choose delta equal to epsilon, then this is satisfied. So it seems kind of convoluted if you're not used to the definition, but let's just argue why it's true. So we can just say let epsilon be greater than 0 and choose delta equal to epsilon. Then if x minus c is less than delta, we have f of x minus L, which is equal to, that's x, that's the limit which we claim is c, which is less than delta, because that's what we're assuming for if that's the case. But we chose delta equal to epsilon. So we've shown that the function minus the proposed limit is less than epsilon, whatever that holds. So that basically establishes part two. Again, it seems kind of like maybe trivial because that's X and that's C, but it's still important to show that, okay, it does satisfy this definition, so part C is true. And then we'll prove part three later in this lecture. Okay. So next, we're going to look at theorem 1.2. Okay. So theorem 1.2. And this, you can think of it, these are like the basic properties of the operations you can do on limits. So let's state our hypothesis first. So let B and C be real numbers. Let N be a positive integer. And let F and G be functions with the limit of f of x as x approaches c equal to L, and the limit as x approaches c of g of x, we're going to suppose that's equal to m. And so we have all these properties that are, we just let those be assumed, and then the actual statement of the theorem goes as follows. So part one, the limit as x approaches c of b times f of x is equal to b times L. Again, b is just any real number. Part two, the limit as x approaches c of f of x plus or minus, it doesn't matter which one, g of x, is equal to L plus or minus respectively m. So the limit of f of x plus g of x would be L plus m. The limit of f of x minus g of x would be L minus m. Okay. Part three, the limit as x approaches c of the product of f of x and g of x is just going to be L times m. Okay. Part four, the limit as x approaches c of f of x over g of x is equal to L over m, provided m is not equal to 0. Right, so when you have a ratio of functions, you can just take the ratio of the limits provided the denominator is not 0. And then finally, part five, the limit as x approaches c of f of x all to the power n is equal to L to the power B. So again, B is just some constant, so the constant times F, take a limit, it's B times the limit, and then all the others are just algebraic properties. Okay. So take a moment to write this down. We're going to be using them quite a bit in this section. Okay, so let's look at an example of how to use these. Say the limit as x approaches 2 of 4x squared plus 3. Okay. So we can use these properties over here to compute limits. And in fact, I forgot, I kind of want to show you how we can prove some of these, maybe that one, the second one. But let's just apply them first, and then I'll show you how to prove at least one of those. So here is our limit, and we have a limit of sums, right? So we have, this is like that right there. You could think of that as like f of x. And that right there, you can think of as like g of x. Okay. So we can apply Theorem 1.2 part 2 and just split this up. The limit of the sum is the sum of the limits. That's what that says. So this would be the limit as x approaches 2, 4x squared plus limit as x approaches 2 of the function 3. Just by applying that rule there. The limit of the sum is the sum of the limits. Okay. So then here, we have a constant times a function. So the constant times a function, that's equal to constant times the limit of the function. So this is like saying 4 times the limit as x approaches 2 of the function x squared plus the limit of a constant is just a constant by Theorem 1.1 part 1. So that's just going to be 3. That's a limit of x to the power 2, which by the previous theorem, Theorem 1.1 part 3, is just like valuing 2 as your x. So is that 4 times 4 is 16. So it's just 19. Okay. So when you have some complicated expression here, and you kind of evaluate a limit, you can partition that expression into pieces according to Theorem 1.2. Okay. That's why this is a useful theorem. To have like maybe like a note card next to you so you can always recall that. Okay. Now, because I would like to show like a little bit of rigor, I guess I will prove this one. So let's prove that. Okay. So let's prove that one. And this is part 2 over here. And again, back to being a data science major, the proof analysis is not going to be the most important thing for you to know, unlike maybe a math major. However, the more math you know and the more technical math you know, rigorous math you know, that will allow you to dive deeper into some of the more sophisticated parts of data science, including machine learning and things like this. So just because I'm showing them to you doesn't mean you're going to always use them, but pay attention to the proofs so that if you want to dive deeper, you can. So, okay. So we're supposing that the limit of f, so let's just do the plus part. Let's do plus. Okay. We're supposing that the limit of f is L and the limit of g is M. Okay. So suppose limit x approaches c, f of x is equal to L, and the limit as x approaches c of g of x is equal to M. Okay. Now, if I had another board, this would be a lot more useful, but I just write down some scratch work over here. So what we want to show that the limit of this is equal to L plus M. That's what we want. So in other words, for epsilon greater than 0, we want to show like this is what we want for some choice of distances around C, right? But this is like saying this, right? Just distribute the negative in. It's like saying the same thing there. Now, there's an important notion in mathematics. It's used quite a bit when dealing with inequalities, and it's called the triangle inequality. So the triangle inequality. And it says that the absolute value of a plus b is at most the absolute value of a plus the absolute value of b. So that's the triangle inequality. The absolute value of the sum is less than or equal to the sum of the absolute values. So that's the triangle inequality. So looking back here, we have a sum, right, of two things. So I can say that this here is at most this by the triangle inequality. Okay. The sum of the the absolute value of the sum is at most the sum of the absolute values. Okay. Now, because we know that the limit of f of x is L, the limit of g of x is M, right? We know that this absolute value is at most maybe like I don't know, epsilon 1. There's some like if you pick any epsilon, we'll get, so in particular, I can pick any epsilon and I know that that's going to be at most that epsilon, right? So I'm going to say that can be less than epsilon, and this right here can also be less than epsilon. Because we know that goes there and that converges there for x going to c. So we know if we pick an epsilon, we can find a distance around c. I'll call that delta 1, so that that's true. And then we know for this one, there's a distance around c. I'll call that delta 2, so that that's true. And for any epsilon, we can find a distance around c so that that's true. I call that distance around c delta 1 for the first part. And then here, I know for any epsilon, there's a distance around c. I call that distance delta 2, so that if this is true, then that's true. If that's less than epsilon, and that's less than epsilon, then that sum is at most 2 epsilon, which that's like choosing any positive number again, because epsilon is any number, so twice of it doesn't matter. Or I could say, I can make that epsilon over 2, like that. Because for any positive number I pick, I can find an interval around c, so that this holds, or this is at most that number that we picked. I pick epsilon over 2. I pick epsilon 2 there. I know the same things hold. So when we add these together, we get epsilon. So this is like a scratch work behind finding the proof of that statement up there. So maybe when I write it out in more detail here, it'll make more sense. So we suppose this is true and that's true. Next, let epsilon be greater than 0. And observe there exists delta 1 greater than 0 and delta 2 greater than 0, so that f of x minus L is less than epsilon over 2 whenever x minus c is less than delta sub 1, and the absolute value of g of x minus L is at most epsilon over 2 whenever the distance from x to c is less than delta 2. Right? That's by definition of the limit. You give me any positive number, if the limit of that goes to L, if f goes to L, any positive number, there's an interval around c, so that if x is in there, then that is a hold. Epsilon over 2 is just some positive number, so we know that this must hold. Okay? So notice that the intervals here are dependent on the delta. So if x is in this interval, then that one's true. If x is in this interval, then that one's true. Okay? So if we want to choose both of them, if we want to satisfy being in both of these intervals around c, we just take delta to be the minimum of those things. So I'm going to say choose delta equal to the minimum of delta 1 and delta 2. then if x minus c is less than delta, f of x minus L is less than epsilon over 2, and g of x minus m. Oh, wait a minute, that should be m right now. Is at most epsilon over 2. Sorry, g converges to m, not m. So, if x is in this interval, then it satisfies being in here, and it satisfies being in here, which means that that's true and that's true, which is what I wrote down. Right, because delta is the smaller of these two, so we're guaranteed that if x is in there, it must be in there and in there, which means that that must be true and that must be true. And then we could say something like hence, or therefore, or anything along those lines. The absolute value of f of x plus g of x minus L plus m is equal to f of x minus L plus g of x minus m, which by the triangle inequality, the absolute value of the sum is at most the sum of the absolute values. Okay. And then we know that f of x minus L is less than epsilon over 2 whenever x is in that interval. So this is at most epsilon over 2. And we know that if x is in that interval as well, g of x minus m is at most epsilon over 2. But that equals epsilon. And this holds whenever x minus c is less than that delta that we take right there. This delta. So the sum minus the sum of the limits in absolute value is at most epsilon for any epsilon greater than 0 whenever x is in this interval. And just remember that that delta was the min of delta 1 and delta 2. Which that means that we've shown it to be true. We've shown that that is at most epsilon, which that proves that statement. Again, it's very mathematically rigorous and proof-oriented, but this is a part of calculus in a sense. It's not the main part for you by any means, but it is a part. Justifying these claims is an important step in any of your upper-level mathematics course, or at least like thinking about it. You have a question?
Yeah, there's two words that I can't read. It's beside next let delta or epsilon greater than 0 or
Yeah.
and what is that?
Observe. Observe. Observe.
Thank you.
And the other word?
Yeah, the one at the very right. It looks like home.
Oh, hence.
Hence. Oh.
Yeah. Okay, so that's just a proof of one of these statements, which, by the way, the proof of this statement implies 5 for sure, right? Because you take the sum of 2, which is the same as the sum of 3, so forth and so on. And if you take the sum a certain amount of times, you can use additive properties and get to this one. And then a few other results. This is like the main collection. Okay. So as a consequence of these rules, 1 through 5, we have the following theorems. So just recall the definition of a polynomial function. So just recall that a polynomial of degree n is a function that looks like this. So n is a positive integer, a sub I is just some real number. Yeah, so this is a polynomial. Most of you should be familiar with polynomials. So theorem 1.3 states that, so if p of x is a polynomial function, and c is a real number, then the limit as x approaches c of p of x is equal to p of c. So you can just plug in the limiting value provided as a real number whenever you have a polynomial function. Now, as a consequence of this, we also have that if r of x equals to p of x divided by q of x, where p of x and q of x are both polynomial functions. So this is a rational function. So it is a rational function. Then the limit as x approaches c of r of x is equal to p of c divided by q of c, provided q of c is not equal to 0. Okay. So, and then let's write down one more theorem. This is 1.4. So let n be an integer, or a positive integer, then the limit as x approaches c of the nth root of x is equal to the nth root of c is true for all c when n is odd, and all c greater than 0 when n is even. So it's important to note that if this number is negative, then we can't take that negative root, the nth root of that negative number in this formula. Okay. Okay. Okay, and then let's say one more theorem to write down before we do another example. So theorem 1.5. Okay, so if f and g are functions with the limit as x approaches c of g of x equals to L, and the limit as x approaches L equals to f of L, then the limit as x approaches c of the composite function f composed with g equals f evaluated at L. Okay. So these are just tools. Again, these are tools. If we have polynomials, it's really easy to evaluate the limit. You just plug in your value for c. If you have rational functions, you plug in your value for c into the numerator and denominator, provided you have a non-zero denominator. Square roots, plug in again, provided c is greater than 0 or n is even and c is greater than 0. And then here we have a rule for composites. So all of these theorems are just pointing towards giving you various tools to just calculate limits by hand without having to prove anything. So let's look at like an example. Maybe say, let's look at the limit as x approaches 3 of the cube root of 2x squared minus 10. Okay. So what can we do here? So this is like a composite function, right? So f of x is equal to the cube root of x, and g of x is equal to 2x squared minus 10. So f composed of g is precisely this function here. So let's see if it satisfies the conditions. So we see that, so the limit as x approaches 3 of g of x, well, g of x is just a polynomial, right? So we can just plug in 3 into that polynomial by theorem 1.3, right? So here is plug in a 3, and we get 2 times 9, right, which is 18 minus 10, and 8. Okay? So now, so that's the limit as x approaches c for g. So now we need to look at the limit as x approaches 8 of f. Well, f is just the cube root of x, so the value in here, our c, is 8. So it's positive, right? So then we can just say, oh, the limit of this is just the nth root of that. So this is like saying the cube root of 8, i.e., which is 2. So the limit of the composite then, according to this theorem, is just going to be root 2. There you go. Okay. All right. Okay, so let's look at our next problem now. So suppose we have function f. It looks like this. Okay. So this is equivalent to the function make sure I wrote that right. So make sure so x. You just verify this. I forget all the time. So x squared, x cubed. Plus just x to the 2 x's. No, just x. Yeah. The x times that is x squared minus x squared minus 1 combined with 3. Okay, so this is just another way of algebraically expressing the function f. But then notice that x minus 1 divided by x minus 1, that is just a 1, right? So we can say that when you divide out, you get a new function, call it g of x, which is equal to this function here. Okay? So you can only divide out x minus 1 divided by x minus 1 whenever x is not equal to 1, right? So if x is not equal to 1, that's the only case this makes sense. So this is, in fact, a different function from that function, even though when you simplify this ratio, they become the same. This is what's called a removable discontinuity. So what do these functions, like, what do the graphs of these functions look like? So x is 0 right here, and then something like that, maybe. Something like that. So this would be f of x, and then g of x would look with that whole filled in. This is g of x. Okay. So notice now that these functions differ at exactly one point. Namely, x is equal to 1. So f of x and g of x differ only at x equals 1. But just looking at these pictures here, we see that as we approach 1 from the left and the right, we're approaching this limit. And that limit there is precisely g evaluated at that missing point. Okay. So this leads us to our next theorem. Okay. So this is theorem 1.7. Now notice I skipped theorem 1.6. I need you to go into the textbook and read that theorem. It concerns the limits of the basic trig functions. But as we'll find out, if a function is continuous on an interval, then you just plug in the value c and you get the limit. So we can come back to that theorem in the next step. Okay, but theorem 1.7. So let c be a real number and let functions f of x and g of x equal, so let f of x equal g of x for all x not equal to c in some open interval containing c. Okay, so it's just like this scenario here. So the only difference is here I didn't use an open interval, but if I just put like an open interval like that, then everything about that hypothesis is the same. So the statement of the theorem says that, so if the limit as x approaches c of g of x exists, then the limit as x approaches c f of x equals the limit of g of x. Again, as x approaches c. Okay, So that pictorially is exactly what we described here, right? F of x and g of x differ at most one point in this interval, namely x is equal to 1. So if we look at the limit as x going to c, it equals L here for g of x, which means that this is going to have the same limit, which makes it really easy now for evaluating the limit of f of x, because g of x only differs from f at one point. So then the limit as x approaches 1 of g of x, in this case, is 1 plus 1, so it's 3, which means by theorem 1.7, the limit as x approaches 1 of this statement here is going to be equal to 3. So it's like an application of this theorem is given with that function f. So in general, if you can remove a discontinuity and get a simple function, just like we did here, we had a discontinuity and we removed one of those discontinuities and we got some simple polynomial, we can just plug in the limiting value. And then since that function differs by at most 1 from that function there, 1 value x, then we can just say that they have the same limit. So this is a technique for finding limits where you need to remove discontinuities, basically. That's what that theorem is giving you. Okay. So that was an example illustrating this theorem. And it's a technique. It's a technique of eliminating these discontinuities, dividing out the factors which lead to division by 0. Another technique is given by rationalizing ratios. So we have a limit, and if x goes to 0 of the square root of x plus 1 minus 1 over x. Then if we try to like plug in x, we get division by 0, which, as we recall from theorem 1.5, I think, part 6 maybe, you can evaluate ratios, but you need to avoid division by 0. And also, we see that there is a square root here. So what we're going to do is we're going to get rid of the square root by multiplying by a fancy version of 1. So what you can do is multiply by this. Square root. Y'all should agree that this is equal to 1. It's something divided by itself. So when we do this, and we can always multiply this by some constant number into 1. So this limit is going to be the same thing as saying the limit as x approaches 0 of, so let's work this out. Square root of x plus 1 times square root of x plus 1 is just x plus 1. Square root of x plus 1 times 1, right, which is plus root x plus 1. Then minus 1 times that is just minus root x plus 1. And then we get a minus 1 at the bottom. And then here we get x root x plus 1 plus x. So if we simplify this out, we get the limit as x approaches 0 of, simplify the numerator, that minus that is 0, that minus that is 0, just left x. And then in the denominator, we get x root x plus 1 plus x. And then if we plug in x equals to 0, well, actually, we can simplify this out even more. X divided by, so I should just leave it like this so you can see it better. Like that. So then this will be and then we see x divided by x, and we're left with the limit as x approaches 0 of 1 divided by root x plus 1 plus 1. And if you plug in x equals 0, now you don't have a problem. You get 1 divided by, so that becomes root 1, which is 1, so you get 1/2. By first rationalizing and then dividing out the ones. Okay, what's this? Oh, the squeeze theorem. This is theorem 1.8, which is typically referred to as the squeeze theorem. All right, so it states that, so if h of x is less than or equal to f of x, which is less than or equal to g of x, for all x in some open interval, containing C, some real number C. So this holds for all x in some open interval containing C, except possibly at x equals C. So except possibly at x is equal to C. Then if the limit as x approaches C of h of x equals L, which is equal to the limit as x approaches C of g of x, we have the limit as x approaches C of f of x equals L. This is called the squeeze theorem. So why would this make sense? We're not going to prove it, but we're going to argue why. So it's much off. So suppose this is like my h of x, and suppose this is like my g of x, and we have the h of x is less than or equal to f of x, and f of x is less than or equal to g of x. So if that's h and that's g, say this is c. So f is like in here. It's always, so this is f of x. So as you can see, f of x is squeezed in between h of x and g of x. You see that, right? If f is always less than or equal to h and greater than or equal to g, and if h and g both converge to L as x approaches c, then f has no place to go but to also converge to L. And that's why it's called the squeeze theory. Okay. Okay. So, and we'll do more problems with the squeeze theorem next time. I think that's enough for today. So now I'm just going to give you some practice problems to work on. So practice homework. So maybe something like, no, I'll write them over here. I'm going to write down a few for you. And actually, I'm going to go ahead and stop the recording here. Not the Zoom lecture, but just the recording. The recording, just so you can see the problems I want you to work on after today's lecture. And these will be posted on YouTube, so you don't have to like rush too fast to copy them down.